and welcome to our fixed effects models lecture. This is lecture one. We're going to continue fixed effects next week. This lecture sets the foundation for a variety of things that we're going to do throughout this class and a variety of tools that we're going to use. In the end, we're going to combine fixed effects and random effects into a hybrid, holistic approach to thinking about these complicated questions. The other thing I will mention is last week we talked about generalized estimating equations, and generalized estimating equations are ways that we can understand the marginal model, the between model. Today with fixed effects, we're really going to be focusing on the within model, the conditional model. And so these tools really allow us to separate this between and within. And I mentioned that in the beginning of this class. I mentioned it every week, and I'm going to continue to mention it because it's really important that what we have done when we move to a nested structure is we have identified that there are differences that can be modeled between groups and differences that can be modeled within groups, and we really need to start thinking flexibly about that. And today we're going to dig into the within flexibility. Now, we've had this conversation before, and I have this slide, and I've put this slide in various places. This is a slide that is designed to demonstrate that you are not the only people confused about fixed and random effects. They are confusing in themselves, in part because, as we will get to the end of this class, we're going to just throw them all together in one big hopper. There is a variety of definitions of what these are, and you can read there's 5 definitions here. I don't particularly find any of these very compelling. They all tell me something a little bit about it. I have been distinguishing between things in themselves and things that are modeled as distributions, and I think that's a very practical interpretation, and that's the one I will continue to go with. But just suffice it to say that that's not the only interpretation, although you can see that here. Today we're going to really focus on a practical definition of fixed effects. So just to orient us toward the problem we have some set of error terms conditioned on a set of x's that still have a correlation within them. That is the nesting function. We think that these variables, these errors, are grouped in some way not accounted for by our x variables. Now notice I said not accounting for our x variables, conditioned on our x variables, right? That's an important piece of what we're going to talk about today. So we need some way to address this correlation where this assumption is violated. And we've talked about random intercepts, which we call variance components, and we'll spend more time in this class, a lot more time in this class, talking about random intercepts. We talked last week about generalized estimating equations, which take the covariance within the group, treat it as a nuisance, model it out, and get us the between effects without any bias associated with this covariance within cluster. So we just model away the covariance within cluster. We create a covariance matrix that takes that out, and then we can get good standard errors and parameter estimates and beta estimates, our mean model, for whatever it is that we're looking at. So that's the between model, right? Like that GE allows us to get rid of the within problem, throws it away, and then we can look at the between problem. We're going to do the opposite today. So if we have some variable that we can use to model the correlation within groups, we can use that to correct for the OLS assumption. You will note up here I said conditioned on x's, right? So if we can find some variable that represents the group that models away the correlation, then this problem in the error term goes away. Well, it just so happens that we have a variable called groups, right? Or ID, which are either persons or cities or some geographic unit other than cities, or clinics or counties, or whatever it is that we want to do. Time, persons nested in time. So, or items nested in times, right? So there's some group variable that we can create that allows us to adjust for the within cluster correlation. So we can solve this problem that we have here by just finding a new x that does that. And that's what fixed effects are. Fixed effects just find some x that accounts for this correlation or nesting structure. And since we already have one in all of the models that we're doing, whether it's generalized estimating equations or random intercepts or fixed effects, we can just actually model that away. Now, there's some problems that come up with the parameterizations, with some parameterizations, and we're going to talk about a variety of different ways to do this today. But suffice it to say, what we are doing is identifying the group and saying we're going to take out the effect of the group. And by doing so, we are only left with the within part. And we are getting rid of the between part, the exact opposite of what we did last time. Last time with generalized estimating equations, we got rid of the within part and just had the between part. Today, we're getting rid of the between part and keeping the within part. All righty. So let's take an example. The panel crime data is, we've dealt with this data at various points in time. We will continue to look at this as an example. It's a simple sample of crime rates per 1,000 and unemployment rate is traditionally measured in 46 U.S. cities. The data collected is at 2 time points, 82 and 87. And the question that we're going to ask is, does unemployment cause crime? So the first thing we could do, which we all know is wrong, is run a cross-sectional model. So here I just have 1987, right? I just said that I just want the year 1987, and I want to predict crime rate as a function of unemployment. We get our intercept, right? That is here, and we get our beta coefficient for time, for unemployment, and that is here. So that's the exact opposite of what our hypothesis would be, because I'm going to bet when I said we were going to look at whether unemployment predicts crime, most of us thought that increasing unemployment, right? Increasing unemployment increases crime. We thought that there was a direct relationship, but you see here there's a negative coefficient. There's a sign that suggests that increasing unemployment that is a weird one, decreases crime. That's not what we want. That's not what we want. So that's against what our hypothesis is. We'll also note that it is not statistically significant. But we didn't expect to really be able to detect that in cross-sectional data, in large part because we have combined the within and between effects. We don't really see any within effects. We only see between effects. So this represents differences in cities with varying rates of unemployment and varying rates of crime. And I don't exactly know why this is negative. This is not my area of study, but hypothetically, for example, let's say that places with high unemployment don't have a lot of things to steal, and so there's not much crime to commit. So as unemployment goes down, crime goes up because that Lamborghini is a little more tempting than a 30-year-old gremlin, right? I don't actually know if gremlins are even 30-year-old. If you don't know what a gremlin is, you're too young. It was an old bad car. Or Pinto, another great bad car. So maybe what we're seeing here is the mean effect between cities, but its relationship is not entirely clear because what we're really interested in is how does the change in unemployment produce a change in crime? And that is a within effect question, not a between effect. We are not interested in, do cities with high unemployment have high crime? Maybe or maybe not, but that's not what we're interested in. We're interested in, does change in unemployment cause crime? And so that's a question we're going to need longitudinal data for. And fortunately, we have longitudinal data. So obviously, this model does not allow for statements about change in how unemployment affect crime. It only allows for comparisons between cities. What we want to know is the change piece. Does change in unemployment affect change in crime? And so in order to do that, we need to identify the within-city change and compare that within-city change between cities. But it's the within-city change that we want to compare. So fortunately, in this case, we do have longitudinal data. We have 2 time points. We have 1982 and 1987, and this allows us to separate things that are consistent, things that stay the same within cities, which are the between city differences, right? Because if it's the same within city, there's no within comparison, there's only between comparisons, from the things that change, which are the changes within cities. So we're going to compare the between to within. I promised you, the only thing we're doing in this class is between and within, between and within. And here we are again, comparing between and within. And we're going to pull out the between, leaving the within. And we're going to do that through several different mechanisms. So the language we've used so far is to separate the between model from the within model. And that's what fixed effects allow us to do. All right. So how would we do that? Well, the one model, which is called the dummy method model, dummy variable method, is to create dummy variables for the within effect. And that is this coefficient here, alpha sub I. And all that is a dummy variable for each city. And you can see here when we run it, all I did here is take the city variable, which is just, 1 through 46. You see there's 92 observations here because we've got 2 time points for each one, and 96 times 2 is, or 46 times 2 is 92. So all I did is just estimate an effect for city. I estimate an effect for time because I want to take into account the 2 time points. And then I'm predicting the crime rate by the unemployment rate. So I have created 2 different fixed effects, one for city and one for time. And that allows me to model out the effect of time and the effect of city, leaving only the within city effect. And so when we do that, right, we still have, we'll have an intercept, and we'll talk about what that is. We have our time variable here, and you can note that by the time, right? So this is our coefficient for time, and this is the actual time, and time is just 0, 1, with 0 being 1982 and 1 being 1987. So I just created a variable that did that. And then we have unemployment, which varies between cities and within cities, between and within. And then we have an error rate between and within as well. So when we estimate this model, we get, I'll note it's a very high R squared because each city has its mean. So if we sort of do what we've always done before, we start with the intercept. What does this intercept mean? This is the crime rate for city number 1, which was left off in 1982. So this is the crime rate with 0 unemployment. With 0 unemployment. This is the crime rate with 0 unemployment in city 1 in 1982. These, you'll notice I have a bunch of dots here because this goes 2 down all the way to 46. So that's a long list in the actual data output. I'll show you in a second. So city 2 has a much higher crime rate than city 1, substantially higher. So for city 2 in 1982, the expected value of crime is 145 per 1,000 when unemployment is at 0. As we move to time 2, which is denoted 1, which is 1987, we have to add 15 units. So crime goes up in between 1982 to 1987. And then again, we can go back and calculate the mean value for crime in 1987. But I will note that we have now estimated the effect of unemployment on crime, and it's positive. So as unemployment goes up, crime goes up, and it's now statistically significant. So we have isolated the effect of time because we've taken out what is essentially allowed here is each city at each time point is allowed their own intercept. Each city at each time point, and we just went through the mean there, right? The means. Each city at each time point is allowed their own intercept. So adjusting for each city's average crime rate, we can now look at the effect of change in unemployment on crime because we have isolated out the between effects. These are the between effects, and we've controlled for the between effects, and all we are left here with is the within effect. The great thing about this is we control for all the between effects, not just the ones we've identified in this data set. We have controlled for everything that is static, whether you're in the Northeast or whether you're in the South, whether you have a hot climate or a cold climate, whether you have a high proportion of white folks or a low proportion of white folks, whether you have an old population or a young population. As long as those things don't change over time, And certainly between 82 and 87, any change in the demographics or age distribution of a population is probably a very, very small change. And certainly things like the physical location of the city don't change. The the history of redlining in the city doesn't change. A lot of that stuff is going to stay pretty constant between these two time points. Anything that is the same between these two time points is now controlled for, all of it. The only thing that's left are varying things. So great news. We controlled for a whole bunch of stuff that we don't know about. We don't even have to know what those variables are. We don't even have to know what the between confounders are. We've controlled for it by including city and time coefficients. We've controlled for all of it, leaving only unemployment here in this context, but everything else that is changing. So the only thing that now is going to affect crime we're going to be able to isolate the effect of change in these variables, obviously other things are changing and we don't have them in the model, so we're not adjusting for those, but we have adjusted for everything that's static, and that is a huge benefit for fixed effects models. All right, so let's walk through this a little bit differently and see what we did here, because I made some pretty strong claims that we have isolated the effect of change, and we can do that by looking at the equations. Now these are simple equations, right? So here's for 1987. I put that on top, so just note that this is 82 on the bottom. So time 1 is on top, time 0 is on bottom. So this is the time effect for 87, right? We talked about that here, right? This value is 0 for 82. So this coefficient, because it's multiplied together, is 0, right? So this coefficient delta naught only shows up for time 2. So this is the intercept for time 2. This is the intercept for time 1. This is the intercept for each city, right? And this is the intercept at time 2, right there. This is the intercept for each city at time 1, right? So we have all of that. We have our time varying variable, and you'll note that these are different. There's a 2 and a 1, so these are different values because they vary over time. It's unemployment, and unemployment has changed between time 1 and time 2. We have two different error terms for these models. So we have a part of the intercept that's the same and a part that's different. And the part that's the same, when we subtract these, goes away. We are only left with the part that's different, right? Because this cancels and this cancels, leaving only that. The alphas cancel, so they go away. So that's not in here. We are left with the difference between these two, which is what I said. We are measuring the change in unemployment between cities, and that's this thing, right? Literally the change. And that's what this coefficient is, the coefficient for the change. And then we have our error term would be this. And so we're predicting the change in crime by the change in unemployment. And we've isolated that effect. So what I was telling you is true. We can walk through this example as many times and you'll see the same answer. Change in y is a function of the difference in intercepts between time, the change in x between time, and then we still have the error term that allows for change over time. And this is called the first difference estimator. So this is one way of doing a fixed effects model when we have a simple 2 time point case. Let's see what happens, and this is now a limitation of this model. Let's see what happens when we add something that doesn't vary between time, like the area of the city. Maybe we have a hypothesis that larger cities, physically larger cities, have more crime than physically smaller cities. But the area of city doesn't change as you move between time 1 and time 2. It stays the same because the area of the city is a fixed entity. And so any coefficient that we have here is going to cancel out when we subtract, and just like the alphas go away and this beta naught goes away. So even if we put in a variable, For area into our model, we're still left with the same equation. We can't estimate the effect of something that doesn't change over time, or its effect doesn't change over time. That second part is going to come important later. And you can see that by just putting it in here. So I ran the same model, I put in area, and it's omitted. Why is it omitted? Because it's completely collinear with this. These values are 1, 2, 3, 4, 5 up to 46. This is some other number, but those numbers are completely 100% correlated because they don't change within, this doesn't change within city, right? This is city 2 at time 1 and time 2. This is city 3 at time 1 and time 2. And city 2 has the same area at time 1 and time 2. And city 3 has the same area at time 1 and time 2. And so this is like, you can't do that. These are the same thing. You can't put that in there. So it just omits it. It physically won't do it. And you can see here why. Because this cancels out. So what we are doing here is we are taking out the within effect, the between effect, by modeling this. So anything that is a between effect, and area, because it doesn't change, is a between effect, goes away. We cannot model that. Now, if you think about persons, for example, it's going to be difficult to model race, or the effect of race, or the effect of starting age, or the effect of parents' education, or something else that doesn't change between time points. And that's a limitation of the fixed effects approach. The good news is that we've controlled for all of those things. We just can't identify what those things are, but we've controlled for all of them. So there's a trade-off in information and efficiency. So we're very efficient at getting rid of those problems, but we lose the information associated with which problems are important. And that may or may not be of value to you. All right. So let's switch examples here. I want to use the National Survey, Longitudinal Survey of Youth example. That was the example actually you used in the homework this week. The dependent variable is antisocial behavior. There are two independent variables that I want to look at, poverty and self-esteem, and then we'll look at some other things. Self-esteem higher is better, poverty lower is better, not surprisingly. Antisocial behavior is not good, so what our hypothesis is that higher poverty is associated with higher antisocial behavior, and higher self-esteem is associated with lower antisocial behavior. So that would be the working hypothesis for what we're doing here. All right, so let's run our two separate models. So we're just going to isolate 2 years, and then we'll build up. So this is 90, and this is 94. We estimate the model with that as an intercept for 1990. We estimate the effect of self-esteem, and that is right here. We estimate the effect of poverty, and that is right here. And then we have an error term. So interpreting this is higher self-esteem is associated with lower antisocial behavior, not surprising. Troublingly here, higher poverty is associated with higher antisocial behavior. So poverty is related to antisocial behavior, self-esteem is both related, and we see that effect down here as well, right? So both of these are statistically significant. They move in the same direction. They're of similar magnitude. But all we've said here is that there is an association between poverty and antisocial behavior and self-esteem and antisocial behavior. What we want to know is, does self-esteem changes in self-esteem produce changes in antisocial behavior, and do changes in poverty produce changes in antisocial behavior? That's a causal statement. The first statement, these cross-sectional things are just correlations. They're just associated with one another. But if we want to isolate a cause, we need to find some way of adjusting for those mean differences between people and looking at the relative differences within person. How does a change in person's self-esteem or a change in person's poverty affect antisocial behavior? Because that tells us about the causal relationship between self-esteem and poverty with antisocial behavior. So I did that same subtraction that we did before. I just subtracted the intercepts. I didn't put a time variable in here, so the intercepts went away. So here we have the well, we have the mean difference in intercepts here. This represents the mean difference between time one and time two. Here is the effect for the difference between between self-esteem. Here's the effect for the difference between poverty, and here's the effect for the difference between this is our error term difference, right? So now what we see is that changes in poverty don't affect, notice it's not statistically significant and it's much lower. Changes in poverty don't affect antisocial behavior, but changes in self-esteem do. Now, how did I do this? How did I operationalize this in Stata? Well, that's pretty straightforward. So here's by the way, here's the crime analysis that I showed you before. These are all pretty straightforward. I just estimated an effect for time and city. I could have had an I here on time, by the way, or factor or class for those of you in R and SAS respectively. So I'm going to use this national survey data. And this is the first two regressions that I ran, right? So you can see the effect here. And those are the same models that we saw before. And then to calculate the difference model, literally what I did is I took a difference. I will note that this data is wide, not long. Wide, not long. This is the, I just took the difference between time 1 and time 2 for antisocial behavior, the difference between time 1 and time 2 for self-esteem, the difference between time 1 and time 2 for poverty. And then I just ran a regression with them. And these differences, so I just isolated the differences. I demonstrated previously that that's what we were doing up here as well, right, with those formulas. But here I just literally did it, and you can get these coefficients. So it's really a straightforward approach when you have 2 time points. Now, all right, so let's add something that is not changing over time. Let's see if we can add race to this. So in the first parameterization, we looked at, we got rid of the between effects by directly modeling them, and these are nuisance variables. We're going to throw these away. We generally aren't super interested in the effect of these. We're really only interested in the effect of unemployment in this context. But the way we parameterize this makes this variable completely collinear with this. The way that we just learned how to do by getting the difference between the time 1 and time 2 variables, that potentially has the ability to allow us to do it because we don't have that same problem. We're just running, we've gotten rid of the alphas. We've canceled that out. We've gotten rid of the sameness of the intercept, and we're left with the difference in the intercept. And so we can actually model the effect of the difference here. Now, I will note that when you multiply all this out, you get several different variables, and let's just walk through that. I'm sorry, when you subtract this out, right? So we're subtracting this from this, and that gives us this. We're subtracting these two, and because we have a difference here and a difference here, what we end up with is the coefficient for the difference. This is the difference between them. And then here is the difference in coefficients between the time 1 variable. And we're going to do this combination for both self-esteem and poverty. So you'll notice here the difference, the coefficient for the effect of the difference is for self-esteem is here. And that's that variable that we created. This we're just going to model by saying, okay, the effect of time 1, right? And looking at how the effect of time 1 affects the change. That's this over here. So we're just going to put in the self variable for time 1, right? So there's the change and then the baseline. And that's the change and the baseline. We're going to do the same thing for poverty. Difference poverty and difference and baseline poverty. So that's how we get those two. And then we have this set of things. Now, here we're going to call this race. And we saw before, I don't know if I can write with this pen. Oh my goodness. So I want to note the question we're asking here is a little different than the question we asked before. Before we were asking, we wanted to know, does area affect outcome, affect crime rate? But we didn't allow for the difference, but we didn't allow the effect of area to change between time 1 and time 2. Here, because we're modeling the difference, we are essentially modeling that. Is there a difference between the parameter at time 1 and the parameter at time 2 for this one variable? And we do that by just putting the variable in there. But that's because we've got this difference over here. That's because we're modeling this difference over here. You'll notice this is going to be run in just regression, right? So this is now just a cross-sectional data set of the differences between time 1 and time 2. And so we can get the effect and test whether the effect of race changes between time 1 and time 2. And it turns out that the effect of race does not change between time 1 and time 2. These are not statistically significant, suggesting that there's no reason for us to model this. We can model it by getting the differences here. And the differences, as we pointed out before, allow us to control for these, allow us to control for the between effects by isolating only the within effects. All right. So it's a relatively simple example in the case of 2 time points, but what do you do when you have more than 2 time points? So we could extend this out further. It seems complicated and unnecessary, and since nobody ever does that, I think we're going to move to the way that most applications, and certainly R, Stata, and SAS all do it this way, is what they do is they take the difference of the observations from the mean within cluster. So each of the within cluster observations are subtracted from the within cluster mean. You'll note that that's the exact same thing that we just did, but with 2 time points, you just subtract them from each other. But when you have more than 2 time points, you construct the mean, and then you subtract them from the mean. Now we could do this by hand, but that's going to give us the wrong answer. And the reason that it's going to give us the wrong answer is because we have degrees of freedom problem. So the software adjusts for that, and that's what we're going to use. But and I think this is where it really becomes much more clear about what I'm saying when I say that we're going to subtract the between effect from the within effect. So the means, right? And here we've got an intercept. Let's start with the dependent variable. We've got the average within cluster for y. So there's just one variable per y. There's no time subscript here, right? So this is just the average outcome variable within cluster, the intercept, the average whatever x variable within cluster. We have this between cluster effect, and then we have the average and the average within cluster error. So this is the between model, right? This is just the between model, because this is, if we had 5 observations per person, we would only have 1 mean model per person. So now we're back from a longitudinal data set to a cross-sectional data set. This represents the average difference between persons model, and we just subtract that from this. And by subtracting it, we literally subtract it, right? So we subtract these 2 terms, and we subtract these 2 terms, and they go there. These cancel out when we subtract them, and so that goes away. These don't cancel out because they're different terms. And so we now subtract the average of whatever variable from the particular observation. And then these, because they're the same, they cancel out. And then we're left with this set of terms. So by taking the average, we are left with that there's only the within model. All of the between stuff has been taken away. That gets us back to controlling for all of the things that are the same within time between cities. So anything that is consistent, that is a consistent difference between cities or persons or whatever unit, Whatever is consistent is gone. Now remember, that's consistent both in terms of the value itself and in its effect over time. So the change in effect over time has to be consistent, and the change between and the value itself has to be the same. So both of those have to be the same. Those are all controlled for, so that's great news. And we're only left with change over time. Now the great thing is, and this is the way GenMod or even GE can do it, GenMod or Proc GenMod or Proc GLM in SAS. There's several applications in R. I don't know what they're off the top of my head, although I will find them out before we meet on Friday. In Stata, it's called XTReg. And the first thing we do, and if you did the homework this week, you know that you have to do XTset. So you do XTset, and then you do XTReg, and it does all of the differencing for you. And you'll notice here we get the same answer that we got before when we ran this model. This is our interclass correlation. It's the shared variance at the cluster level, so there's a lot of person level cluster. But this is all taken out, and what we see here is that because it's a fixed effects model and it's the FE, you can also run a random effects model incidentally in XTReg, although we'll be using mixed for ours. But here you have the effect of self-esteem, which is higher self-esteem lowers antisocial behavior, which is in the consistent direction. We have the effect of poverty, so increasing poverty. At least the coefficient works in the same direction, although it's not statistically significant, suggesting that there's not much difference. So this is the way that people do it in the real world. We've walked through the example from first differencing to mean differencing, which is traditionally called the fixed effects estimator. But that's what we do here. Now, incidentally, you might be asking, whoa, you said no constant. This is the average effect across all the persons. So this is the average. This is the average of the alphas across the persons, and that's just the way they parameterize the model. But suffice to say, we've gotten rid of all of the between person effects, all of the things that are consistent between persons. And we've already identified race as something that's both consistent. Obviously, people's race doesn't change for the most part. But the effect of race over time also doesn't change. So we don't need to have race in here. We are already adjusting for race by taking out the between effects. We have already adjusted for race. We've already adjusted for differences in age, since the relative difference in age doesn't change. Does the effect of age change over time? That's a separate question, which we will look at in a second. But gender, for example, mother's socioeconomic status, neighborhood characteristics, assuming people don't move neighborhoods, like all of that stuff are adjusted for in these models, and we have isolated only the within person effects. All of the between person effects that are static both in effect over time and in value over time are controlled for. All right. So in the previous example, when we looked at this data with the parameterization of just 2 time points, we were able to identify, we were able to produce evidence that there was no change in coefficients between Hispanic and whites and blacks and whites in the data, and we did that by directly modeling it with that particular parameterization. Here we have to do that in a slightly different way by interacting with them with time, but we end up getting the same answer and the same effect. So let's head on over to Stata. So first of all, as I mentioned, this data is wide format currently. If you look at it, right, anti-90, anti-92, and anti-94 are next to one another. So I need to do a couple of things to get this data set ready to analyze in XTMix. So the first thing I do is I create a variable that is my ID variable, and I just do it this way. Every software program has a way to do that. I'm then label this variable so I know what it is later. I'm not confused. And then I'm reshaping to long, and poverty, self-esteem, and anti are the variables that are going to be nested within each other. If you look at the variable list, things like black, child age, that's child age in 1990, gender, Hispanic, whether the mother is married in 1990, mom's age at the birth of the child, whether the mom works. It's a static unemployment variable. It doesn't change over time. These are all non-changing variables, so I don't need to put them here because it knows that it's the same. There's no difference between them. But poverty, self-esteem, and antisocial behavior are going to change over time, right? And so I'm going to say they're nested within ID, and then the variable, how they have the names with 90, 92, and 94. So I'm going to call this, going to extract these guys as it stacks them on top of each other, and it's going to create a variable called time or year that says 90, 92, and 94. And that's what this code does. Again, all the software does this reshaping. It works. Excellent. Now, I'm going to create a time variable. And basically what I'm going to do is create a 0, 1, 2 variable. I do it in, there's tricks for how you do all of these things. In Stata, what I do is I say, create a variable called time that if this logical condition is true, it's 1. If it's false, it's 0. So 92 is going to be 1. 90 and 94 are going to be 0, right? So if it's 92, it's going to be 1. Everything else is going to be 0. And then I replace time equals 94 with 2. And that just allows me to do it in 2 lines of code as opposed to 3 lines of code if I did it the other way, or one of the other ways. And then I'm going to do xtset. And here we are. And now this is the model that I just showed you, right, with poverty, self-esteem. We can add time into this model and look at how these variables change over time, and you can see that that antisocial behavior tends to increase over time. That's the evidence here. So there's time 1 and time 2. There's very little difference, but time 2 from time 0, there is a statistically significant difference, which is not surprising. Antisocial behavior is a lot of things like drinking and other things like that that are totally varying with time. Which brings me to the question that I want to ask, which is, we know that race is likely not to vary with time, and this is just repeating the same thing that we did before. But the age of the child, right? So this is the age of child in 1990. So it's a non-time varying variable. But if we interacted with time, what we're asking is, does the effect of child's age change over time? Which is the same question we were asking before in the other parameterization, by using the first difference parameterization. Here, in this parameterization, we're going to have explicitly an interaction term. But we're asking, is the coefficient, so that the value of child's age is not different. It's the same, right? So it's the age at 1990. It stays fixed. It's one number for each person. It doesn't vary within. What we're asking here is, does the effect of age change over time? Does being a young person's effect on antisocial behavior, is that different than being an older child's effect on antisocial behavior? And for that, we run that interaction. And I just use the Stata interaction function. You can do it the other way. You will note that it's omitted because that doesn't change over time, and so you can't see the effect there. And same with Hispanic, and same with child age. Just like in the dummy coding parameterization, we couldn't see that effect because it doesn't change over time, so there's no variability. It's collinear, so it's omitted in this. But what we do get is the effect of the change over time. And here we see, consistent with what we saw before, that there is no statistically significant difference for race, either for Hispanic or compared to white, or black compared to white. So the effect of race is consistent across time, and because of the way we parameterize this model using only within effects, we've controlled for race, whether or not we put it in here, but we don't have to adjust for the effect, the interaction either. So I would probably get rid of this if this were my model. But child age does change over time. So you see here, the difference between time 1 and time 0 is not statistically significant. But once they reach time 2, so I don't know what age they were at the beginning, 8, so like 8 was a common age, right? So by 1994, which is the latest age in our data set, that person is 14 years old. Wait, so 8, in 1990. No, so 12 years old. And I think there were some older people as well. So yeah, so we're starting to get into the late tweens, early teens when we get to time two, and that's when you start to see the effect, the relative difference in child's age affecting it. So small changes in time, in age, are going to have an effect because of this interaction in time. So as the children get older, those relative differences in age really matter, and that again, this is not my area of study, but if I were the one doing this study, I would start thinking about this is around the threshold. Like somewhere here is a threshold where children move from non-differentiated in terms of risk of antisocial behavior to differentiated between these children. So it's right in this critical threshold, right? That 11, 12, 13 time when children move from not being at risk for antisocial behavior or for escalating antisocial behavior. So there's a threshold here where I would start worrying about kids and doing some intervention. But we've been able to put back change over time by modeling an interaction. So we've seen two different ways. The first, difference parameterization, which works when you have 2 time points. And here, when we have multiple time points, we have to interact the variable with age. I will note that these are basically the same thing. All right, so take-home message for fixed effects models. They control for all non-varying effect. And when I say non-varying effects, what I mean is the variable itself doesn't vary, and the effect of that variable over time doesn't vary. Just like we explored with child and race, the effect of race is consistent across time, and so there's no evidence that it varies. We don't need to have race in these models because we're already adjusting for it by adjusting for the between person variability. We've adjusted for all the between person variability. I didn't test the model for gender, but maybe we could do that in the class and see. And does the effect of gender change over time? But what we did identify is that the effect of age differences between persons change over time, and that as we get to the older person, so 11, 12, 13, somewhere in there, there's a big difference between an 11-year-old and a 12-year-old. And that tells me there's a threshold there, and we should probably be thinking about that. But we only know that because we interacted time with a static variable. So we can do some pieces, but it's a very specific question that we're asking because we've gotten rid of all the between-person effects that don't vary. So the great thing is that this doesn't assume that the group effect is uncorrelated with the other independent variables. We treat it just like a regression parameter. Now, with random intercept, we're going to have to be cautious of that because our random intercept, just like our error term, is not allowed to be correlated with other independent variables. And that's a strong assumption to say that your group effect, that your person effect isn't correlated with other variables that you have in your model. So we're going to have to be cautious of that. Now, the hybrid approach that we're going to end up with is going to allow us to mix these, but and capture the benefit of each of them. But for now, let's just say that the fixed effects model, while controlling for between level effects, has the benefit of not violating assumptions of independence, because just like all of your other dependent variables are allowed to be correlated with each other, your alphas are allowed to be correlated with each other. That's not true of random intercepts. It's great for modeling change over time. As you can see here, we can really isolate the effect, the within effect, the change over time within group. And if those are your questions, if that's what you're interested in, fixed effects are a fantastic approach to that. So we're going to take some more time next week and expand on fixed effects. We're going to look at this from a structural equation modeling perspective, which is going to really help us understand the hybrid model later. And we're going to take a look at some limited dependent variables, specifically logistic regression and count models, and how we can model those using fixed effects. All right. Thank you very much.